One process, 246 services, all running inside this single process, right now on this Raspberry Pi. Every notification you have ever received, every app that ever launched, every window that ever appeared on an Android screen, all of it flows through this process. System server, the process we dissected in episode 12. But in episode 12, we saw system server from the outside. We saw that it starts 246 services. We saw the boot phases from 0 to 1000. Today we are going inside. We are going to understand the most important service living in there. The one that manages every single app process on your device. The one that decides which apps leave and which apps die when memory runs low. We are going deep into Activity Manager Service with real source code, real numbers, and real live output from this Raspberry Pi. Welcome back to Android Internals from Scratch. We are from Must Electronics. And if you have been with us from episode 1, you know exactly what we did with Raspberry Pi 4. A Raspberry Pi 4 running Android 14. Not a stock ROM, not a pre-built image. Android we downloaded, built from source using Soong and Ninja, and flashed ourselves. Every process running on this device, we can trace it back to a file in the AOSP repository. Let me quickly recap the last 4 episodes because today builds directly on all of them. In episode 9, we trace the full boot sequence. Stage 1, bootloader loads the Linux kernel. Stage 2, kernel creates init as PID1. Stage 3, init reads init.rc files and starts Zygote. Stage 4, Zygote preloads 17,182 Java framework classes into memory. Stage 5, Zygote forks System Server, its first fork. Stage 6, System Server starts all framework services. Stage 7, Launcher appears on screen. Today we are living inside Stage 6. In episode 10, we learned init is PID1. If it dies, the kernel panics. It reads .rc files, mounts file systems, and starts Zygote as a managed service. In episode 11, we learned Zygote is the app incubator. It preloads thousands of Java classes once, then forks child processes. Each fork inherits all of that preloaded memory instantly through copy on write. Zygote's first fork before any app is System Server. In episode 12, we learned System Server runs 246 services as threads inside one process. It goes through boot phases. At phase 1000, Android considers itself as fully booted and launcher appears. Today we are answering these 5 specific questions. Number 1. What exactly are framework services and why do they exist? Number 2. How does System Server organize 246 services at startup? Number 3. How does any app find and talk to these services? Number 4. What does Activity Manager Service actually manage? Number 5. How does Android decide which app to kill when RAM runs low? And we are answering all of this with real source code from AOSP and live command output from the SPY. Let's go. Let's start the concept. No code yet, because if this is not crystal clear, nothing else will make sense. Think about every interaction you have with Android. You tap an icon, something decides to launch it. You install an APK, something scans and registers it. You rotate the screen, something repositions all windows. You press the power button, something dims and locks the screen. You get a notification, something decides where to show it. Your RAM fills up, something decides which app to kill. You connect to Wi Fi, something manages the connection. All of those somethings are framework services. Framework services are the middleware layer of Android. They live between your app and the operating system. They have two critical jobs. Job 1, expose APIs to apps. When your app calls start activity, that call goes to Activity Manager Service. When your app calls get package info, that goes to Package Manager Service. When your app calls get system service, that fetches a reference to a framework service. Your app never directly touches hardware. It never directly touches the kernel. It talks to a framework service. The service does the real work. Job 2. Enforcing system policies. Which app gets CPU priority right now? Activity Manager Service decides. Which process gets killed when RAM runs low? Activity Manager Service decides. Who is allowed to draw on the screen? Window Manager Service decides. Who can install an APK? Package Manager Service decides. Who can start a background service at 3 a.m.? Activity Manager Service decides. These are policies, rules about how Android behaves. Without framework services enforcing these rules, every app would fight every other app for resources. Android would be chaos. Now, here is something important that trips people up, even experienced developers. The third point in the not list is one of the biggest confusions in Android. When developers hear service, they think of start service, foreground services, background services, service.java. That is completely different. Framework services are not started by apps. They are started by system server at boot. They live forever. They manage the entire Android runtime. Let's see them on our Pi. 246 services in total, two parts on each line. Left side is the service name, the key any app uses to find it. Activity, package, window, audio. Right side in brackets is the binder interface, the list of methods this service promises to handle. Android.app.iActivityManager tells us Activity Manager service implements every method declared in that interface. We will look at that interface later. But first, how do all these 246 services get registered? And how does any app find them by name? That is the job of SystemServer's three-phase startup. SystemServer.java, the entry point for everything that starts at boot. Let's find the run method. This is where SystemServer's life begins after Zygote forks it. Three phases, three method calls. This is Google's deliberate design. See that last line. Throw new runtime exception. That line should never execute. If looper.loop ever returns, something catastrophically wrong happened. System server is supposed to run forever. The moment it stops, Android is dead. Notice also the system service manager. This is the manager of managers. It creates service instances, call their lifecycle methods, and send them boot phase signals. Every service goes through it. Let's see each phase. Bootstrap services, the absolute foundation. Nothing can start without these. Look at what starts first. Watchdog. Not Activity Manager Service, not Package Manager Service. Watchdog. Watchdog is Android's self-monitoring system. Every critical service, including Activity Manager Service, registers with Watchdog. Watchdog runs a health check every 60 seconds. If any registered service fails to respond in time, Watchdog triggers a full system reboot. Android kills itself rather than limp along with the broken service. Think about how seriously Google takes the reliability of these services. They would rather reboot than let a broken Activity Manager service corrupt data or leave apps in a stuck state. Next comes Package Manager Service. Because even starting other services needs to find components, verify permissions, and locate APK files. Package Manager Service must be alive before almost anything else can work. Then Activity Manager Service, the engine, and Power Manager Service must come before any display work because the display code needs to signal system wake and sleep through Power Manager. Core services, important but not foundational. They need bootstrap services to be ready first. Battery tracking, app usage statistics, WebView updates. These are the services that keep Android healthy and up to date. Start other services. Window Manager service comes here after Input Manager is ready because Windows need to receive touch and keyboard events. Display is already running from Bootstrap. Input is fresh. Now Window Manager service can manage what appears on screen. Then comes everything else: network, audio, notifications, storage, Bluetooth, location, printer. Every feature users expect from Android. All started in this one method called Cascade. Now, after all these services start, how does any app in the system find them? How does your code reach into System Server and call Activity Manager service? That is the Service Manager. Think about a city phone book. You look up a name, you get a phone number, you dial that number, you reach the person. Service Manager works exactly like this. Services register by name, apps look up by name. Let's see both sides. ServiceManager.add service. Activity Manager service says, "Hey Service Manager, my name is Activity. I am registered. Whenever anyone in this system asks for activity, give them a binder reference to me. From this moment on, any app, any service, any process in the system can reach Activity Manager service by looking up the string activity. One string. That is all it takes. Your app calls get system service. Context IMPL asks Service Manager for activity, gets back a binder reference, wraps it in an auto generated proxy, returns the activity manager your code uses. Every method call you make on that activity manager, start activity, kill background services, get running app processes, crosses the process boundary via binder, and lands inside activity manager service running in system server. Completely transparent. We cover binder in full in upcoming episodes. For now, let's verify this is real. Real. Working. Service manager confirmed. Activity, window, audio, all registered and responding. Does not exist, not found as expected. Now let's go inside the most important one, Activity Manager Service. Before we even open the file, let's understand its scale. 128 files just in the AM directory. The AM package, Activity Manager. Activity Manager service is so large that Google needed 128 separate files just to organize them. Let's look at the main file. 20,876 lines. One file. An average Android app, the entire codebase might be 5,000 lines. Activity Manager Service main file alone is 4 times that, and it has 127 more supporting files. This is not bloat. Every single line exists because Android's process management is genuinely this complex. Let's look at why. Three things in this one class declaration. Each one tells us something critical. First, extends iActivity Manager stub. Activity Manager service is a binder service. iActivity Manager stub is auto-generated from the AIDL file. It contains all the method skeletons that apps can call. Activity Manager service overrides every one of those methods with the real implementation. When Service Manager adds service, registered this is the binder object apps talk to. Second, implements Watchdog Monitor. Activity Manager service registers itself with Watchdog. Remember Watchdog that we discussed before. Health check every 60 seconds. If Activity Manager service hangs, Watchdog triggers a system reboot. Android deliberately reboots rather than let a frozen Activity Manager service leave the system in a broken state. Third, implements battery stats IMPL battery callback. Activity Manager Service reports battery impact for every process state change. Every foreground service that starts, every background wake that happens, Activity Manager Service tells battery stats. That is how settings. Battery screen knows which apps are draining your phone. 5 areas, each one complex enough for its own series of videos. Notice what I said about activity management. It is delegated to Activity Task Manager Service, which is a separate service. Two services. Activity is Activity Manager Service. Activity Task is Activity Task Manager Service. This split happened in Android 10. Before that, Activity Manager Service did everything including managing the activity stack. The file was becoming unmanageable even by Google standards. They extracted Activity Task Manager Service specifically to separate concerns. Activity Manager Service coordinates. Activity Task Manager Service handles tasks and activity stack management. They work together constantly. But Activity Manager Service is still the senior service. It makes the decisions about processes. Activity Task Manager Service makes the decisions about activity organization. Now let's look at what I think is the most brilliantly engineered piece of Activity Manager Service and one of the most important algorithms in Android, the OOM Adjuster. Here is a question every Android developer has faced, whether they realized it or not. Your phone has 4 gigabytes of RAM. You have opened 30 apps today. 30 apps times an average of 200 megabytes each. That is 6 gigabytes needed. But you only have 4. What happens? Does your phone crash? Does it show an error? Do you have to manually close apps? No, none of that. Your phone just works seamlessly. Android kills apps, but not randomly, not arbitrarily. Activity Manager Service has a precise, calculated, continuously updated system for deciding which app gets killed, in which order, based on how important each process is to you right now. This system is called the OOM Adjuster. OOM means out of memory. The OOM adjuster assigns every process a score. The score ranges from minus 10,000 to 1001. Lower score, the process is safer. Higher score, the process dies first. This is not estimated. This is not approximated. These are the actual constants from processlist.java in our AOSP Android 14 source tree. Let me show you. Real constants. Let me explain the most important ones. Foreground app ADJ 0. The app you are using right now. Score 0. Maximum protection among app processes. Activity Manager Service will not kill this. Perceptible app ADJ 200. You can perceive this app is running. A music app playing audio in the background. A navigation app giving directions. You would notice if it died. Activity Manager Service protects it accordingly. Home App ADJ 600. The launcher. Score 600. Activity Manager Service gives it special protection because killing the launcher would leave the user with no home screen. But it is not as protected as the app you are currently using. Cached App LMK First ADJ 950. This is a crucial constant. LMK stands for Low Memory Killer. It is a kernel level daemon. This score 950 is the line in the sand. When system memory drops low, the LMK starts at score 999 and kills downward. It kills everything above 950 before touching anything below 950. Cached app LMK first ADJ is the threshold where the kernel's killer first becomes active. Cached app max ADJ 999, the most expendable cached process. Nothing between 950 and 999 survives under serious memory pressure. Unknown ADJ 1001. A process that is terminating or in an unknown state, essentially already dead from Activity Manager Service perspective. Let's verify this with real processes on our Pi. System server itself, PID 721, OAM score minus 900. That matches system ADJ from processlist.java exactly. The kernel will never touch system server. If somehow it dies anyway, the system reboots automatically. There is no graceful recovery from a dead system server. COM Android DYN system. Score 965. Above LMK threshold of 950. This is cached, empty, and frozen. If RAM pressure spikes, the LMK will kill this first. Notice, is frozen is true. Android 12 introduced process freezing. A frozen process gets 0 CPU time. It cannot execute any code, but it stays in RAM. If you switch back to a frozen app, it is still in memory and comes back fast. Freezing reclaims CPU without losing RAM state. Only when the system needs the RAM does it fully kill the process. Another one, score 955. Also cached, also frozen. This process became freezable 41 minutes and 9 seconds ago. Activity Manager Service tracks this to the millisecond for every process at all times. It knows not just what state each process is in, but how long it has been in that state. How does Activity Manager Service communicate these codes to the kernel? When Activity Manager Service calls process.setOOMADJ, that call writes directly to the kernel via proc PID OOM score ADJ. We just read system server's value minus 900. That is the value Activity Manager Service wrote. The kernel's LMK reads these value for every running process when memory pressure is detected. Activity Manager Service is the judge. It calculates and assigns scores. The kernel's low memory killer is the executioner. It reads scores and kills. They work together. Neither knows what the other is doing in detail. They communicate through a single file, OAM score ADJ, in the proc file system. Elegant and simple at the kernel boundary. The OAM score is what Activity Manager Service writes to the kernel. It is the kill priority number. But Activity Manager Service also tracks something more nuanced internally, process states. These are Activity Manager Service own classification of why a process matters. Not just how much to protect it, but why it should be protected. There are 21 of them. 21 states, unknown at -1, non existent at 20. The pattern is clear. Higher number means less important. State 2, process state top, the app you are currently using. Maximum CPU scheduling, minimum OAM score, maximum memory budget. Activity Manager Service treats this process as the most important non system process alive. State 11, process state receiver, a process executing a broadcast receiver. Android gives it temporary elevated priority for the duration of the broadcast. When the broadcast finishes, its state drops back to wherever it was. State 14, process state home, that is the launcher. Not as important as the current app, not as expendable as cached apps. Special treatment because users need a home screen. State 19, process state cached empty. We saw this on our Pi. CUR proc state 19, cached, empty, nothing bound to it, nothing using it, just RAM. First category to be frozen, first category to be killed. State 20, process state non existent. The process is dead. Activity Manager Service keeps the record temporarily for bookkeeping after a kill. This state exists so Activity Manager Service can clean up gracefully. Let's look at the real output again and read it fluently now. When all three process state fields match, CUR proc state, MREP proc state, set proc state, the system is stable. No transition happening. When they differ, Activity Manager Service is mid transition. Changing a process importance is not instantaneous. Activity Manager Service recalculates, propagates the change, waits for the process to acknowledge, then confirms. Those three fields track that three-step handshake. Before we leave the process management section, one more piece. Android does not immediately kill cache processes. It has one more trick first: memory compassion. User compassion true. Memory compassion is active on this spy. Compact throttle 1 5000. 5 seconds after a process enters cache state, Activity Manager Service runs partial compassion. Compact throttle 2 10,000. 10 more seconds, Activity Manager Service runs full compassion. Compassion uses ZRAM, a compressed area within RAM. Android takes the cached app's memory pages, compresses them, and moves them into ZRAM. The app is still technically in memory, but takes up a fraction of the physical space. Compact throttle min OOM ADJ 900 only compacts processors with OOM score 900 or above. Those are our cache processors with scores 965 and 955. Android's memory management philosophy in sequence. First, freeze the process. Reclaim CPU. Keep RAM. Second, compact the process. Reclaim RAM partially. Still recoverable. Third, only if RAM is critically low, kill the process outright. Kill is the last resort, not the first. Activity Manager Service orchestrates all three steps. I want to show you something from our Pi that I think will genuinely surprise you. System Server PID 721. The same process we have been talking about all episode has 305 broadcast receivers registered. 305 different broadcast actions that Activity Manager Service is watching for on behalf of System Server. Screen off, screen on, action shutdown, user removed, secret code. These are the events that System Server cares about. And look at System UI 120 receivers. The phone app 43 receivers. Activity Manager Service is managing all of these simultaneously for every registered receiver across every app in the system. See required permission. Activity Manager Service checks this permission on every broadcast delivery. If the sender does not have Android permission control in call experience, Activity Manager Service blocks the delivery. No exception, no workaround. Activity Manager Service is the gatekeeper. This is broadcast security. Apps cannot broadcast to permission protected receivers without holding that permission. Activity Manager Service enforces it before the receiver ever sees the broadcast. Every single time. Every broadcast in the entire system flows through Activity Manager Service. Every single one. Send broadcast, send ordered broadcast, send sticky broadcast. All of them arrive at Activity Manager Service first. Activity Manager Service decides who gets it, in what order, with what permissions checked. No broadcast skips this. Ever. Now let's look at the fifth responsibility: content providers. The settings content provider. Authority settings. This single provider serves settings data to 17 different app processes simultaneously. System UI is connected. Network stack is connected. Settings app itself is connected. Phone app, Launcher 3, Permission Controller, and so on. Activity Manager Service knows all of these connections. It tracks when each connection was established. Look at those timestamps. Plus 2H43M59S for System UI means that connection has been active for 2 hour 43 minute 59 seconds since boot. Why does Activity Manager Service track content provider connections? Because content provider connections affect process importance. If a cached app is providing data to a foreground app via content provider, Activity Manager Service knows that. It elevates the cached app's OOM score. It will not kill it, while the foreground app depends on it. Activity Manager Service sees the entire dependency graph of your Android system. Every process, every connection, every dependency, continuously in real time. This is the contract between every app in the system and Activity Manager Service. Every method Activity Manager Service offers to the world is declared in this file. 969 lines. Just the interface. The list of method names, their parameters, and their return types. Not the implementation, just the declaration. Activity Manager Service implements every single one of these 969 lines. 20,876 lines of implementation for 969 lines of interface declaration. Every method you have called from an activity manager, every context method that touches Activity Manager Service, it maps to a method declaration in this file. AIDL, Android Interface Definition Language, takes this file and generates two Java classes at build time. iActivity Manager stub, the server side. Activity Manager Service extends this. iActivity Manager stub proxy, the client side. Your app gets this. When you call any method on Activity Manager, you are calling through the proxy. The proxy serializes your call, sends it via binder. Activity Manager Service stub receives it, deserializes it, and runs the real implementation. Your app start activity call leaves your process, travels through dev binder, a kernel driver, arrives inside system server's address space. Activity Manager Service executes the real logic. Result travels back the same way. Your app gets the return value. Your process and system server never share memory directly. The binder driver mediates everything. This isolation is fundamental. A crashing app cannot corrupt Activity Manager Service. Activity Manager Service can kill your process without dying itself. Activity Manager Service can inspect your process from the outside. Security and stability flow from this architectural decision. We will go through Binder in detail in upcoming episode. For now, let's do one last live verification with our Pi. M focused app. Activity Manager Service knows right now that Launcher 3's Quick Step Launcher is the focused activity. Task ID 16. This gets updated instantly every time you switch apps. Activity Manager Service knows which activity is on top of which task at every moment. This is how it calculates foreground app ADJ. This is how it knows which process gets OAM score 0. This is how the entire process priority system stays correct in real time. Let's bring everything together. That was Activity Manager Service, one service of 246. And I want to be honest with you, we only touch the surface. Activity Manager Service also manages ANR detection, the complete foreground service enforcement policy, background execution restrictions tied to battery optimization, content provider permission enforcement, and the intricate dance of starting a cold app that has never run before versus resuming one from cache. Each of those is deep enough for its own video. But now you have the foundation. You understand how Android thinks about processes, how it protects what matters, how it kills what does not, how apps reach into system server and pull out capabilities, how 246 services coexist in a single process without stepping on each other. In episode 14, we go into three more services that are equally fascinating. Package Manager Service. Every installed app, every permission, every component, every intent filter. We will trace what happens from the moment you tap install on an APK all the way to the app appearing in your launcher drawer. It is a fascinating process that touches Package Manager Service at every single step. Window Manager Service. Every window on your screen is managed here. We saw in the DUMSys output that Window Manager Service knows about launcher, status bar, input method, and wallpaper. We will go inside that and understand how Window Manager Service decides Z order, how it handles window animations, and how it connects to Surface Flinger. Power Manager Service. Wake logs, screen timeouts, dose mode, standby buckets. Everything about how Android extends your battery life lives in here. We will look at the real power state on our Pi and trace how a screen goes from on to off to dose and back. Drop a comment below. Which of the three services are you most excited to see? Package Manager Service, Window Manager Service, or Power Manager Service? If you found this video useful, please like the video and subscribe to Must Electronics.